Okay, so in this video, we're going to quickly walk through the equations of motions for a simple pendulum, skipping some of the details, which I'm sure you'll be happy to know are going to be part of your homework assignment, that you're going to have to fill in some of these details. But the idea here is, here are some variables at play. So we've got the length of the pendulum is given by L. We've got the mass of this bob over here. We call the end of the pendulum the bob. So it has some mass. The theta is the same as before. It's giving our position relative to its equilibrium. And this S parameter over here is like the arc length, that it's the distance that the pendulum has moved. And so this arc length we can find by multiplying the angle, if it's in radians, times the length of the pendulum. And so there are a couple of forces acting on the pendulum. One of them is gravity. And so the force due to gravity is given by this force over here coming straight down. And that force due to gravity we could write as minus m times g, which is a constant of gravity, times the sine of theta. So that's something that I'm going to ask you guys to just verify in the homework. And the hint here is that it's just going to depend on doing some trick with this triangle over here. So you want to find the length of this side of the triangle, for example. The frictional force, which you can think of as like the air resistance. So this pendulum is rotating around through some medium. You can think about it in like a swimming pool, for example, but usually we just do these in a room, and there is some friction due to the air resistance as it bobs back and forth. So the frictional force I'm going to ask you guys to derive is going to equal to minus b times L times d theta dt. So L, again, is the length of this pendulum, and B is a constant. This is what would be like the damping coefficient for the mass spring oscillator. So this is relating to some sort of resistance from the air. The force generated by the bob, right, using Newton's second law, that's going to be the mass times the acceleration. So the mass is a constant m. The acceleration we can write as the second derivative of our position. So the distance that we've traveled is s, and then our acceleration is going to be the second derivative of that. And again, using some of the geometry over here, we could show that this is equal to m times the length of the pendulum times the second derivative of the angle with respect to time. And so if we balance all of these forces out, which needs to happen, then the force generated by the pendulum is going to equal the sum of the forces. Here are two of them acting on the pendulum, so here and here. So basically, I would set this equal to the sum of this and this. And to make things a little bit simpler, we can divide everything by m over L. And you guys will be able to verify that we could rewrite the equations of motion like this. So here our variable is theta, that's changing with time. B is the damping coefficient, m is the mass at the end of the pendulum, L is the length of the pendulum, and G is denoting the constant gravity. And so we're going to, in order to simplify this a little bit, since we have so many constants, let's say that the length of the pendulum is equal to gravity, in which case this coefficient over here is going to be 1. And in addition, if we assume that the mass is 5 times the damping coefficient, in other words, B divided by m would be 1/5, and that's going to give us this coefficient over here, therefore it would be 0.2 if we write that as a decimal. And so now we could write this equation as theta double prime, second derivative of theta, is equal to minus 0.2, first derivative of theta, theta prime, minus 1 times the sine of theta. Okay, so here we've made some, we've set the values of some of these coefficients just to cut down on the number of letters in that equation. So we have this second order differential equation for theta. And what's really nice and useful tool is that any second order differential equation we can write as a system of two first order differential equations. And the advantage is we've already talked about a lot of techniques that we can apply to systems of first order differential equations. So if I define the first derivative of theta to be v, then notice the second derivative of theta would therefore be the first derivative of v, right? Since the second derivative of theta is like the acceleration, and we can just write that as the derivative of the velocity. So now my second equation would be v prime is equal to, and I have minus 0.2 times theta prime. So instead of theta prime, we just defined theta prime as v. And then we've got minus the sine of theta. So now I've taken the second order differential equation, which is governing the motion of this pendulum, and I am able to write it as a system of two first order differential equations. However, this differential equation is nonlinear because we have this sign over here. So just be aware that this is nonlinear. So some of the techniques that we've been using with linear first order differential equations, we're going to have to see how they might be able to help us in a situation where we have a nonlinear system. So I skipped some of the details here about how we can derive these equations of motion because I want to have you guys try and do that as one of your homework problems. But if you have any questions on it, you certainly can let me know.